Okay, in this section 4.5 for Advanced Algebra 2, we're talking about mathematical modeling. So I'm going to give you two examples of mathematical modeling and how it's used. So the first example is this thing with this lumber, the piece of the wood problem. Okay, so you are given a piece of 12-foot lumber, so here's the picture. How can you cut the lumber to create a rectangle of maximum area? How do you know, and then how can you prove it? And so before we begin, it's good to note that the way that the lumber is going to be sitting next to each other is like this little arrow over here. So they're sort of just butting up to each other right there. They're not overlapping on one another. And then so as an example here, here's what I did. So here's this Diora's example right down here. I said, okay, well, what if I cut the piece of wood by 1 foot, 1 foot, a 5 foot, and a 5 foot, right? So to create this picture here, right? This guy right here. So then, according to the area formula, the area is just the length times the width. So area would be 5 times 1. So I came up with an area of 5 feet squared in the middle. I blue area here in the middle. And so the question was, can you do better? How do you know? And how can you prove it, right? So we paired off into groups, and a lot of people came up with the right answer. But I just want to explore that answer a little bit more with you. So here's what most people were able to come up with, but didn't really understand exactly how we got there. So let's start by saying, okay, well, the perimeter of my rectangle here has to be 2L plus 2W. And my perimeter is fixed because I have 12 feet, so there's nothing I can do with that. So 12 feet has to be 2L plus 2W. Now I can simplify this and say 6 is equal to L plus W. Right? So that means that if I solve this for W, W is going to be 6 minus L. Okay, so now I have W and L sort of separated on both sides of the equation, so I can plug one in for the other in the area function. So here's the perimeter. Let's focus on the area now. So the area of a rectangle, of course, is the length times the width, right? So the area is going to be the length, but now I can replace width with 6 minus L because I solved for it over here, 6 minus L. So now area is equal to 6L minus L squared. And what this represents, everybody, this is a function of length to area, right? So I'm writing area as a function of length because I have only area and only L, and that length is the length of my rectangle there, right? No, thank you. So area is a function of length. I'll write down area is a function of length. Okay, so what we're going to do is we're going to explore this function and see if we can figure out what we're looking for, right? And the thing that we are looking for is we want to maximize this function, right? We want to maximize the area of this thing because it's an area function. So we're looking for the maximum. So you can use your graphing calculator. I'm going to use fluid math to explore that. So I'm going to bring it up here. And I'm going to use x's instead of l's. So I wrote down the function f of x equals 6x minus x squared. That's the same thing as is over here. 6L minus L squared. I just changed it to x's. So let's explore this, right? So I'll bring the graph up, okay? And you can see, right, it is a parabola. And that makes a whole lot of sense because it's a squared function and it's opening downward because a is negative and so on and so forth. So what am I concerned with here, right? I'm concerned with only the positive x-axis here, right? And notice that it starts at 0 and then ends over here at 6, right? And what this represents for everybody, this represents down here, this is the length, right? And that this way, that's the length, and then this is the area. Okay, so what it seems like the maximum is right about there, right? The highest spot, right? So it seems like when I get a length of 3, I'll have a maximum area of 9. That's what it seems to be. And then how can we check to make sure? Well, we can bring up a table, okay? And we can have that table go from 0 all the way to 6, and we can go by 0.1, okay? And then we can hit OK, and we can see all of the values that we get. Again, so if I have a length of 0, well, I have 0 area, right? 0.1 gives me 0.59. If I have a length of 1, I'll have an area of 5. This was my example right here, cutting a length of 1 and then an area of 5. And as you go down the list here, right, our areas seem to grow and grow and grow until, of course, we get to, check it out, 8.99, and then for 3.0 we get 9, and then right on the other side of that 3.1 it starts to go down again. So it tops out at an area of 9 because this is a function, a quadratic function, has a vertex, and it has a maximum point, right? So that means if I go back over here, I should cut out a 4 pieces of 3 by 3. If each one of these is 3 feet, 3 feet, and 3 feet, 3 feet, then that would give me a maximum area inside of 9 feet squared. And that's how I know, and that's how I can show it. Okay, so a little bit of algebra here relating the two functions together, and then a little bit of analysis using your graphing calculator. And there is a way to get this point on the graphing calculator as well, so I'm going to show you how to do that right now too. And bring it up on the... Okay, so for those of you who have a graphing calculator and want to know how to do this, you can go to y equals, and you can plug in, it was 6x, and then minus x squared, okay? And then we can hit graph, and here's we get the same exact picture, right? But I'm not so concerned with everything to the left of the x-axis or past 6, so I can change my window and have it go from 0 to 6, and we can go by ones, and then the minimum for my y-axis is 0, and I can go all the way up to, I know 9 is the top I need to go, so I'll go to 10. Then I'll hit graph, and I can see that it produces a much better window that's relevant to the problem. So then I can go second and hit trace, and notice down here option number 4 is it will calculate for me a maximum for my function, so push enter. Okay, and you can see right here it's already blinking at the spot. Look, I have x is 3, y is 9. X again is the length of the wood, and then y represents the area. But it's asking me for a left bound, so assuming that it didn't give me the answer right away, I'd go to the left of where I think the highest point is, push enter. Calculator's asking for a right bound, so go to the right of this thing, right? Push enter. Then for some reason it wants me to guess. I don't know. Just hit enter. And again, it gets you 2.999994, and then y is equal to 9. So that's 3, 9. Some people in the class got 3.0001, so I'm not exactly sure why that is. But as you can see, the calculator does also figure out the maximum point, 3, 9. So you can do it with your calculator as well. So I'll put that away for now. Alright, so going back over here to the second problem. Alright, the second problem was this, right, the cardboard problem. It says you find an old piece of square cardboard and you want to make a box with an open top. So what should x be to maximize the volume? How do you know? How can you prove it? So here's this old piece of cardboard that's 12 inches long on either side, so it's square. And we want to cut x out here to create a box with an open top of maximum volume again. So what we want to do, right? Let's go ahead and write down a few things that we know. We know the volume of the thing has to be length times width times height. That's the volume of a box, right? Well, what is the length, right? If I call this length, it's going to be 12, right? Minus this x and minus that x. So there's two x's, right? So the volume has to be 12. Yikes, that's not 12. It has to be 12 minus 2x. That's the length. 12 minus 2x. Well, it turns out that's also the width, since this thing's a square. So the width is going to be 12 minus 2x as well. And then the height, when you fold these sides up, well, the height is going to be however much x is. So the height is x. So all of a sudden I have this nice little function here. So volume is equal to 12 minus 2x squared, since there's two of them, and then times x. So here is a volume function of x, right? Volume is written as a function of x. So volume as a function of x. So that's what that means, as a function of x. Alright, so let's explore this one. And I'm going to use fluid math again. So 12 minus 2x squared times x. So let's go over here. And I brought it up over here on this side. I kind of already had it done for you. So if I punch in, f of x equals 12 minus 2x squared times x, and I graph it, notice I have to go pretty high on my volume, right? Because I'm creating a volume, not area anymore. So not squared, it's cubed now. So I have to go up to about 130 or so on there. So again, this represents the max area. Notice that my domain is from 0 to 6, because once I go past 6, that's more than halfway across the length of that piece of cardboard. So I can't really go past 6 in terms of the practicality of the problem. So this is going to represent the length of x. This is going to represent the volume, right? The length is is independent of the volume. The volume depends on the length, right? So maximum volume looks to be right about there when x is about 2. So if I check on the calculator, I get f of 2 is 128 volume, and I could check just right around there, as a function, what's f of 2.1, and I'll bet you it's smaller than 128, and that is probably smaller than 128. Yeah, I'm sure it is. Yeah, there you go. Here's a decimal form, 127.7. So as soon as you move just to the right of 2, you get something smaller than 128. And what is f of like 1.9? All right. Let's see. Okay, wow, there we go. F of 1.9, approximate answer is 1.27. So you can see just to the left of 2, I get a volume of 127.75, and just to the right of 2, I get a volume of 127.7, but at 2 itself, I get 128. So that seems to be the maximum volume I can get. I can also explore the table. Same idea, right? I'm going from 1 all the way to 6 by 0.1s, and if I go to 2, notice at 2, I get 128, and either side to the left, I get numbers that are smaller than that. So that's how I can show it on my calculator and use it and create a table for that particular problem. So to get back over here, right, the max volume x should be 2, and that produces a volume of 128 inches cubed.